Well, welcome to the BC Calculus video on logistic growth. This is actually our last lesson for covering topics on the BC exam. Logistic growth is a type of growth model. It's a little different than exponential growth, but there are some things that we can kind of use that we can see a little bit about. Exponential growth or decay, as we kind of learned in 8.3 in your AB class, is a situation where the rate of change, whether that's increase or decrease, there's your rate of change, is directly proportional to the population. So it's equal to the population times some constant of proportionality. And we get these exponential, this is exponential growth, but we could have decay graph as well. And that's kind of how those look, and I know those are familiar. Logistic growth is a little bit different because logistic growth is going to recognize that in some situations, the population will start to level off. And we may not just grow forever and forever and forever. We're going to see some examples of that today, but originally when COVID hit in 2020, all of the graphs of the incidences of COVID looked just like this. All of the predictions and the graphs, it was really interesting. They kind of at some point level off because you hit a place where everyone's gotten it or people are immune. And so, or they get vaccinated. And so you stop growing at that rate. And it's kind of interesting. And notice a couple things about this. Part of this graph is concave up. Part of this graph is concave down. So there is a point of inflection for this graph. And that will be true for logistic growth. Unless your carrying capacity cuts on before your point of inflection shows up. The carrying capacity is basically like your maximum population in there, basically. It's called a limiting number sometimes. People often reference it as L. It's because we have limited resources or, you start having a population that stops responding in a certain way. And so what ends up happening is the rate of change of what's happening is proportional to two different things. It is proportional to the population, but it's also proportional to the difference between the carrying capacity and the current population. And that's how we get this kind of unique graph. So here's an example. The rate at which flu spreads through a community can be modeled by this logistic growth differential equation. Now, this is the differential equation, and what you might notice is that this was also a differential equation. When we're looking at logistic growth, most of the time we're looking at its differential equation, not the equation of P, the function, which is kind of interesting. But the derivative, the differential equation, is going to be more useful. So this is usually what we look at. So we have the situation. We're told that this is a logistic model. And notice they are giving us the differential equation. I'd also like to point out, what is P? P is the output. Time is the input. And I'd like you to notice that in the differential equation, only the output is mentioned in this. That's very, very normal. That's what you would expect to have happen in logistic growth. And that's exactly what's happening here. T is our input, but P is our output. But P is actually what the differential equation is in terms of, which is kind of interesting. So taking a look at this one, remember L was called the limiting capacity, or I'm sorry, the carrying capacity or the limiting value. In this particular equation, we can see where that is because it'll be L minus P. So this is L. So for this problem, L is equal to 3,000. Now, something that's interesting is this acts like a horizontal asymptote. And so if we are looking at the limit as time approaches infinity of the function P, which remember, we don't even know that equation, that will always equal whatever L is. So for this particular instance of the flu, the limit as time approaches infinity of the population of people who are getting the flu is going to be 3,000 because that is the limiting capacity. So I'm going to customize this graph a little bit to our flu example. So that would be at a height of 3,000. There's going to be a point of inflection, and it will be exactly at half the height of the carrying capacity. This point of inflection will be at exactly the height of the carrying capacity, or half the height. So if the carrying capacity in this problem is 3,000, this point of inflection would occur at a height or a population of 1,500. Now, I don't know what time that's occurring, but I do know the exact height that it is occurring at. Now, at the point of inflection, P is growing the most rapidly. Why would that be happening? P is growing the most rapidly. Why would that be happening? Well, the second derivative is going to change signs at our point of inflection. Okay, if the second derivative will change signs at my point of inflection, and that's going to happen where the first derivative has an extrema. You might remember that. If we're looking at a first derivative graph of something, let's just say we're looking at an f prime graph. This would be, if we're crossing, this would be a min. We're crossing a min of f. This would be if we're actually crossing, a maximum of f. And this point of inflection, looks like it's right here, would be the point of inflection. This extrema would be the point of inflection of f, a point of concavity changing. So what's happening here is that the second derivative on these graphs, we're changing from concave up to concave down. This is changing. The signs of this is changing signs from positive to negative. We're changing from concave up on P to concave down on P. By the way, just to clarify, this is the graph of P, but I'm looking at the differential equation of it to get information. All right, but the second derivative will change signs from positive to negative at the point of inflection because we're going from concave up to change to concave down. So what happens there on that is that at that same time, the first derivative changes, oh goodness sakes, sorry. This all moved, I apologize. The first derivative changes from increasing to decreasing. So on the first derivative, again, I'm going to have an extrema. And specifically, since I'm changing from increasing to decreasing, the first derivative has a relative max. So that is the maximum, the relative max change. That's why P is growing, this is derivative language, the most rapidly. It's because dt has a relative max at that pi, which is kind of a cool thing that we can find out. Well, let's take a look at example 2. Let's say the number of antibodies, which we're going to call y, that's the output, in a patient's bloodstream at time t, that's our input, is increasing according to a logistic differential equation. Which of the following could be the differential equation? Which of these is in a form? Now, we don't know the numbers, but which of these is in the form of a differential equation? Well, not A. A is not. Remember, we should not be in terms of t, we should be in terms of y, which means we're also going to reject B as well because these need to be in terms of the output. Now, C is in terms of the output, but I don't see where it's proportional to not only the population, but also the carrying capacity minus the population. So I'm going to reject that. These two are very close, but if we look at our form, I want you to notice there needs to be the output as part of the multiplier on the inside, and we're also subtracting the output as well. So we need the population or the output to be here and here. So E is the only one that's in the form of logistic growth. So take a look at example 3. For this one, the population P of T of fish in a lake satisfies this differential equation here that I've given you. Now, this is not in the normal form, which is maybe a little bit stressful for students. What we do know is P of 0 is 4,000. So we're starting out at a height of 4,000, wherever that is. I don't know exactly where that is, but that's our starting height. I'm supposed to, from this, draw the sketch. Well, what I'm going to do is I'm going to work on rewriting this differential equation so that it should be in the form that I want, which is some constant multiplier times P times my limiting capacity minus P. That's what I'm looking for. All right, and I do not want a leading coefficient in here. This I just want minus P only. So in order to do that, if I'm looking at the one I'm starting off with. All right, so this would have to end up being, I have this 3p minus p squared over 6,000. Well, the first thing I'm going to do is I'm going to get these into a common denominator. So right now this has a denominator of 1, so I'm going to multiply both the numerator and the denominator by 6,000. So dp over dt, or sorry, dp dt would then be, looks like 18,000 p over 6,000 minus p squared over 6,000. Now what I'd like is I'd like to use a little bit of creative factoring here. First of all, I want p to be factored out. But I also, I also don't want, and that would allow this to go down to just p to the power of 1. But I also do not want this denominator. So I'm also going to factor out this denominator of 6,000. Like that. So what would that leave me with? That would leave me with my numerator of 18,000, but I factor out the variable p minus p. And this is going to allow me to graph it. My carrying capacity then is 18,000. So whatever, maybe that's 8,000, 12,000, 16,000, 20,000. So my carrying capacity, L, is at 18,000. And my point of inflection is going to be half of that height. Oh, sorry, missed a 0. Half of that height, which would be 9,000. So as this grows, my point of inflection is going to be at 9,000. Now, how far over, right or left, I actually don't know. But what I do know is that's going to be at the height of 9,000. And there's a little sketch for me. So I would like to know a couple things from this. First of all, what is the limit as t approaches infinity of this population? Well, that would be the carrying capacity of 18,000, or L. What is the range of this solution curve? Well, I went all the way down to and including the 4,000, and up to but not including the 18,000. For what values of p is dp dt greater than 0? And how about less than 0? What is it greater than 0, and when is it less than 0? Well, if dyd or dp dt is greater than 0, that's going to happen when the graph of p of t is increasing. Well, in this particular graph, that's happening all the way through. Remember, we're not going to have positive values of or negative values of time. So that's going to happen whenever t is greater than or equal to 0. How about when dp dt is less than 0? Well, that would only happen when p of t is decreasing, which never happens. This is not actually going to happen. So this will not happen. Next question, when is the second derivative of p with respect to t greater than 0? Well, that's going to happen when p is concave up. So that will happen, oops, I kind of wrote this weird, sorry. That's going to happen when p is concave up, and these are the values of p. Oh, that was the values of p, I apologize. So let me rewrite this, I did values of t. That's going to happen when p is from 4,000 all the way up to, but not including 18,000, because this language is in terms of the output, not the input. All right, for E, the second derivative of p will be positive when p is concave up, and that's going to happen on the values of p from 4,000 up to that point of inflection, but not including the point of inflection at 9,000. And then when will this be? Actually, we kind of don't really know what's happening on both sides of that. I'll write that like that. And then how about when is this going to be have a second derivative that's negative? That's going to happen when p is concave down. This is my justification of my answers is describing what's happening with P. And that's going to happen on the interval from 9,000 to 18,000 for P. Remember, these are Y values, output values, not T values. A little bit different here. Assume that P of 0 is 10,000. So maybe our population is not starting at 4,000 for these little fish in the lake. It's starting at 10,000. Is there a point of inflection? Well, remember that at 9,000, we have the point of inflection. If we're at 10,000, we've already passed the point of inflection. So we're not going to have a point of inflection. Now, the carrying capacity is still 18,000. But I'm starting all the way up at 10,000. Wherever that is. I'll land it right there. Well, at 10,000, that's my starting point. My logistic growth graph is going to look a little different here because I'm really only able to look at like this part of the graph. I never get to see the concave up part of the graph because I am before the point of inflection. So the graph would look something like this. Is there a point of inflection? There is no PI since 10,000 is greater than 9,000, which is the location of the PI, because the PI would be half of the carrying capacity or half of 18,000. All right, 2 more examples. Number 4. Why don't you pause the video and give this one a shot and then restart it when you're ready. All right, we are told the rate of change, dp dt, of the number of people entering a movie theater is modeled by a logistic growth equation. The carrying capacity is 500, that's L. At a certain time, the number of people in the theater is 100. Okay. All right, I don't know what time, I just know at a certain time. That is the population. And it's increasing. This is derivative language here. At that instance, it's increasing at 50. That is happening right when P is 100. Well, remember, our formula needs to look something like this. dp dt is equal to some constant of proportionality times P times L minus P. These will end up as variables. I know what L is. L is 500. That's the most people who can be in the theater. What I don't know is the constant of proportionality. To find that, I'm going to use the point that they gave us. They told me dp dt is 50 when we have 100 people. This is going to allow me to solve for K, and in fact, I'm going to replace P with 100 because this is specifically happening when there's 100 people. So 50 would then equal, let's see, K times 100 times 400. And so K would be 50 over 40,000. And if I reduce that and divide by 5, K is going to be 1 over 800. So now I'm looking for the one that has the correct form. Only one of them has the correct constant of proportionality is 1 over 800, and everything else looks good, including my carrying capacity of 500. All right, example 5. Go ahead and pause the video and give that a shot. Number 5, a population Y changes at a rate, it's derivative language, modeled by this differential equation. Notice this is logistic, but they're not telling you it's logistic. All right, so you have to recognize it. We want the values for Y for which the population is increasing at a decreasing rate. What is that? Increasing is derivative language, and so is decreasing. This is increasing at a decreasing rate, so we're taking a derivative again, and we want it to be, in the end, decreasing. In other words, this is telling us that the second derivative here is less than 0. So we want where Y is concave down. Where Y is concave down. Well, what does this graph look like? We have a limiting capacity, or a carrying capacity, a limiting value of 1,000. And so the point of inflection would be at a height of 500. I don't know how far right or left that is. And I don't actually know even the initial value, so I'll just pretend. But it's going to be concave up until then, and it'll be concave up after then. Now, I don't know what time that happens, but I do know what Y values. This will be concave down on the Y values from that point of inflection, but not including it, up to, but not including the carrying capacity. So my answer here is C. And this is the end of your notes for BC Calculus.